Will, are you there?
Yeah, I'm there, Guy.
Will, tell me where you are physically located in the world right now.
I'm physically located in Canberra, Australia, right in the center of the city.
Right in the center of the city. Okay, that's great. And now, Will, I just need to get this out the way straight away because it can be a bit embarrassing, but you are one of my favorite human beings on the planet. For the work that you do with your scientific work. And so I feel like I'm actually speaking to one of my heroes right now. So if I go a little bit gooey every now and then, that's kind of what that's about. Can you, for the audience who doesn't know who you are, just give us maybe just a couple of minute introduction to Will, what you do, and particularly how you got into this particular field of work?
Yeah, well, first of all, my present position is Emeritus Professor with the Australian National University. Emeritus meaning retired. But to go to where I started from and got to be retired, we have to go back to probably around the 1980s when I worked with CSIRO, based here in Canberra. And this was well before we got interested in climate or Earth system science in a general way. But I was working in a relatively minor role with a division that was looking at how the land surface interacted with the atmosphere in terms of transferring energy, water, and very importantly, carbon dioxide. So that was some very fundamental science that I was just getting launched into. But then the big change started in 1990 when I joined probably the first major international program to study things like the carbon cycle and related to climate. It had a very big name, the International Geosphere Biosphere Program. And I was still based in Canberra, but working with the terrestrial ecosystems, the land systems part of it. I think the next big step was in '98 when I was appointed executive director of the entire program and moved my base to Stockholm, Sweden, where I spent 6.5, 7 years as director of the entire program. We looked at the entire Earth system, the oceans, the land, the atmosphere, and so on, how it connected with the physical climate system and how it connected with human systems. So if you like, this was really the origins of what we now call today Earth system science, which of course encompasses climate change, but encompasses a lot more than that. So I came back down to Australia in mid-2004, worked for about 1.5 years with the Australian federal government on climate change issues, and then returned to the ANU, where I started life back in 1977, and became director of a new school called the Fenner School of Environment and Society. But since that time, since the mid-2000s, I've actively kept international connections that I've made, working with the Potsdam Institute in Germany, with the Stockholm Resilience Center, and with others on these broad issues of Earth system science. So that's sort of a very quick, potted background of where I've come from.
Okay, and I know your work, I think initially through the work called the Planetary Boundaries, and yes, more recently, and I'll show you actually, because I think you know this, I use the planetary, because apart from the science work that I do and the communication, I'm a fiction writer. And so I bring the planetary boundaries into some of my fiction works, and I'll show that a little bit later on. But can you tell me a little bit, and what I'm going to do is I'm going to share the screen now, and I'm going to go to the planetary boundaries diagram. I think it's the one from 2013, which is the one that most people use because it's just got the nicest graphics. So just stand by a minute. We're going to share. Okay. Stand by a second. Okay, and I'm going to go back to here, and I'm going to share screen. Okay, and share. Okay, can you see that?
Oh yeah, I can definitely see it.
Okay.
Yeah, that's from the 2015. Yeah,
2015.
Right.
Okay, so can you walk me through just very quickly what I'm going to do? So I'll point to the pieces, and you just give me a little bit of a commentary on it, right? So this is called the Planetary Boundaries diagram, and in a way, if I can just say this, it's always been confusing to me a little bit because the boundary would be technically this blue line or the red line. Okay, is that how we read this?
That's absolutely correct. The planetary boundary itself is where that blue concentric circle is. So we've got 9 major processes or features of the Earth system
Process.
represented
Okay.
here.
Yeah.
Yeah, those are the sort of radial wedges that you see coming out from the center, and there are 9 of them.
Yeah.
And we scaled this diagram that for each one we have what we call a control variable, a parameter that tells you where you are in terms of that process. A good example is atmospheric CO2 concentration for climate. And of course, most people would be familiar with target concentrations and so on. And so we scaled it so where that inner blue concentric circle is, that's where we estimate we should place a planetary boundary. Now, what does that mean? That means that we aim to keep the Earth in what we call a Holocene-like state. Now, the Holocene is the last approximately 12,000 years of Earth's history, and it's been a relatively stable state that allowed us humans to develop agriculture, settlements, cities, complex societies, and so on. And again, if we use climate change as an example, CO2 concentration during the Holocene has been fairly tightly constrained to between 260 and 280 parts per million in the atmosphere. Now, where is that blue concentric circle for climate change? We've actually placed it at 350 parts per million, which is higher than the upper range of the Holocene level, but we think the science tells us we would still have a stable, what we call a Holocene-like state. It won't quite be the Holocene, but it'll be similar. But once you start going out of that, beyond that blue circle, we're in what we call the zone of uncertainty. So we go from a wedge being green, which is the green light, so to speak, in a traffic lights analogy.
Yeah.
Underneath the blue circle, it means we're in what we call a safe operating space.
Yeah.
The space between that inner blue circle and the outer red circle.
Yep.
No, you're not on the red circle yet. Outer red circle, all the way around the diagram.
Yeah, outer red. Yeah.
That one.
Yeah.
The area between those two is called a zone of uncertainty, or I think better, a zone of increasing risk.
Yeah. Yeah.
And it's due to the fact that there's always a bit of scientific uncertainty here as to where we should place that. So we're pretty conservative in where we place the blue circle.
Yeah.
And we're very certain as to where we place the red circle. Outside that, you're in a danger zone, high danger zone.
Yeah.
And in between is a zone of what we call increasing risk. So again, if we go back to climate change, you see we're now in the amber or yellow zone, and we're about halfway up. So we place that inner blue zone at 350 parts per million. We place the outer red zone at 450 parts per million.
Okay.
That is approximately the 2-degree Paris target. Okay?
And is that...
So it lines up that way. And so we are now sitting halfway out there. We're a bit over 1 degree Celsius in temperature rise. But regrettably, that wedge is increasing at a faster rate. Yes. CO2 increasing now at a faster rate than it was 10 or 20 years ago. So that's how the planetary boundary system works.
Okay, and is that parts per million? CO2 or CO2E?
CO2.
CO2. So would you, I mean, you could conceivably amend that to incorporate the other gases?
Yes, you could. We're sort of making an assumption here that, and it is a big assumption, that the extra warming from CO2E, from methane, nitrous oxide, is roughly canceled out by aerosols.
Right, okay.
It's an approximation. And then the assumption is if we could reduce CO2 from fossil fuel burning, we will also reduce aerosols, many of which are associated with fossil fuel burning.
Okay.
At the same time, we also have to reduce the other greenhouse gases. So there is an assumption there that we use CO2 to simplify the whole system here, but it's in the fine print. You can say that you've got to handle aerosols and non-CO2 greenhouse gases consistently with CO2. Okay,
now there's 9 processes in here.
Yes.
Can you explain why there's 9 and there's not 10 or 8? And just that sort of relationship of what is it you mean by processes with respect to this model?
Okay, so basically this was a bottom-up process with a group of experts back in 2007. The idea originally comes from Johan Rockström, who was until recently director of the Stockholm Resilience Center. He's now director of the Potsdam Institute in Germany. But he came up with the idea of saying we should be able to define a limited number of processes that together, including their interactions, define a state-of-the-art system. And so we got a bunch of experts together on oceans, land, element cycles, climate, biosphere, and so on, and just brainstormed at a couple of workshops as to how many processes do we actually need to have to define a state-of-the-art system, and then where might a boundary be placed. So that resulted in the 2009 Planetary Boundaries paper in Nature, which was the first one. So it's a bottom-up process, experts saying, what is the minimum set of processes that you need? Now, you can argue that there could be other ways of coming up with a set of processes, and there probably are. But the point is, there would always be a minimum number. Maybe some people could argue you could get this down to 4 or 5. Others would say, no, you need 12 or 13. But the point is, eventually, when you add up their interactions, you pretty much come up to the same thing. So this is one group of experts' approach to saying, what are the minimum number of processes we need to include to describe the Earth system, how it functions, and what state it's in. So it was a bottom-up scientific elicitation process.
Okay, and so put together, these 9 processes held within that blue line effectively replicate the conditions that we've seen over the last 12,000 years, during which time civilization has grown.
Yes, that's correct.
Okay, that's fantastic. So I find this extremely valuable, apart from the fact that it's actually aesthetically attractive. I find it is very easy diagram to share people, to help them understand, on one hand, that climate change is not just the only game in town, that if we want to maintain a healthy environment, there is these other things. Now, I understand also that you refer to biosphere integrity and climate change as core boundaries. Is that correct?
Yeah.
Can you explain why?
Yeah, what we then did was say, if you held the other 8 constant and buried the boundary of interest, could you throw the Earth system in an entirely new state on its own? For example, land system change. If you push that into the red, deforested the Amazon, Southeast Asian forest, would it push the Earth system into a new state? And the answer is probably not, because if you kept the ocean and the ice and the climate in the green zone, you probably would not. So you test that in each of them. If we push the climate into the red zone on its own, it would influence so many of the other boundaries through interactions that it would throw the Earth system into a new state. Right. Or so. Same with biosphere integrity. And that actually is in keeping when you look at the long history of the Earth system, look at how experts have described the evolution of the Earth system. At its most fundamental level, they describe it as a co-evolution of the biosphere and the geosphere. So think of it this way. Climate change is the most integrative indicator we have for the geosphere, the non-living part, the physical part of the Earth. And of course, biosphere integrity represents the biosphere as a whole. So you could then say that things like land system change feed into biosphere integrity. Stratospheric ozone feeds into the geosphere. Atmospheric aerosols also feed into climate change, and so on. Ocean acidification affects the biosphere. So what we've really come up with are a set of contributing boundaries that we think are important enough in their own right that they need to be here, but they usually act by influencing one of the core boundaries. Now, one of the things we haven't published yet, we've just finished the preliminary research on, is looking at interactions between the boundaries. And we start a priori treating all 9 equally. In other words, don't identifying any core boundaries. And when you look at the interactions, you find that 2 core boundaries fall out of that process, and they are biosphere integrity and climate change. So we think we've pretty much got that right too. Now, hopefully that paper is about ready to be submitted. So hopefully we'll get it in the peer-reviewed literature fairly soon. So I think it's a pretty robust framework that we've developed here.
Okay, great. If I can just recap that. So fundamentally, if you were to hypothetically fundamentally break through one of the boundaries of any of the 7 non-core processes, that wouldn't necessarily fundamentally change the nature of the planet. But if you do break through those boundaries with climate change or biosphere integrity, you're going to end up with a different planet, really.
Yeah, yeah. I think we could say pretty confidently that if you break through one or both of those, you're going to be outside Holocene-like conditions.
Okay.
And we can say we are, because as you see from this diagram here, biosphere integrity is way outside the red zone in terms of genetic diversity. In other words, extinctions are happening far too fast, and so on. And climate change is also outside of the boundary, but within the zone of uncertainty. So we have both of them outside the Holocene boundary. That blue line is a Holocene-like boundary.
Yeah, yeah.
So, and that actually is consistent with this other big development, I think, in the international research community, which is the Anthropocene idea, and the idea that we have now indeed left the Holocene and we're on a trajectory which Paul Crutzen in the year 2000 first called the Anthropocene, and of course that's now stuck and is used quite commonly in the Earth system science community.
Now there was a meeting in South Africa in, I think, December 2016, where that was put to the Geological Union that decides on stratigraphy. So the use of the term Anthropocene, I use it all the time, and it's commonly used. But is the Anthropocene actually now defined as a geological era, or is there still some decisions to be made around that?
Yeah, no, that's an ongoing process. So what was reported in Cape Town was an informal vote of the Anthropocene Working Group. And I'm a member of that group. We still have to go through the formalization process. So what that requires is a couple more steps. One is a formalized vote of the committee, and that vote then is a recommendation that goes up to higher bodies in the stratigraphic community. So it's going to take some years before this process actually works out. But already there are a number of groups around the world who are exploring particular cores, stratigraphic cores in the land surface, in ice, in lakes, lake beds, in coastal seabeds, looking for markers that could be used as the so-called golden spike that would mark when the Anthropocene began. So it's still an ongoing process. What we are unearthing, though, is an absolutely incredible breadth and wealth of interesting markers around mid-20th century, of a real change in human pressures from the mid-20th century onwards.
And so some of those might include plutonium deposits from atmospheric bomb tests?
Yeah, so there are all sorts of different ones. An obvious one are radionuclides from bomb tests, but there are also a number of what we call novel entities in this diagram here. Yeah. Things like plastics, things like aluminium, things like concrete, things like nitrate, and there are a whole range of what we call biostratigraphic markers, things like different new skeletons, say, of domesticated chickens, which now look much different in 2000 than they did in 1900 through genetic breeding and all sorts of things like that. So you can see all sorts of markers of human activity that are developing in the strata as we speak.
And what else would be included in your processes called novel entities? So radioactive material, I guess, is in there. Plastic in the ocean would be novel entities?
Yeah, look, there's an enormous number of possibilities. In fact, the so-called technosphere, the technical aspect of human activity, is exploding at such a rate that we can't keep up. So you've named a couple of them. Plastics are one, radioactive materials another, heavy metals are another. Think of mercury pollution in the seas and so on. Obviously, endocrine disruptors are another one. So there's a whole host of new chemicals that are absolutely novel. They don't occur in nature. They've been made by humans, synthetic chemicals. But then there are other sort of out of the box novel entities. You can think of electromagnetic radiation. Just think of the digital world we live in and mobile technologies. It is flooding the atmosphere with new electronic radiation. And there are obviously concerns about affecting bird migration and things like this. So that's a new one. Artificial intelligence, that's a new novel entity too. And there are concerns about what could happen if artificial intelligence gets out of control. So all of these things, they're new substances in the broadest sense of the term substance that humans are now creating in an ever expanding rate. So that's what we put under novel entities. Our initial emphasis has been on chemical pollutants. But I think we're going to need to expand that as we update the planetary boundaries framework.
Right. Okay. Yeah. Great. Just you mentioned electromagnetic waves. Are you across this? Is it 5G debate? That they've got this new, I don't know, internet technology called 5G, which is apparently everyone's freaking out about. Do you know about that? Are you across that?
No, I haven't seen the details of that, but it's something I need to obviously get up to speed on. I'm still struggling to get up with the novel entities, which are maybe 5 years ago or whatever. Things are changing so fast.
Yeah.
To keep up.
Okay. Okay. Thanks for that. I'm going to go now to your recent paper. I'm going to go back to the share. Stand by again, and go back here, and I'm going to go to there, and then I'm going to go to there. Okay, so this paper here, Trajectories of the Earth System in the Anthropocene. Now, what I understand, I'm just going to go down to some of your diagrams in a moment, but one of the key takeaways that I get from this paper that came out recently is what you're saying is that the climate system has a couple of different phases where it's comfortable to sit, and there's a cool phase where we're sort of in. And then there's a hot phase, which the planet has been in periodically, which basically is very, very bad for the biosphere. Have I broadly got that right?
Well, first of all, I would not say the climate itself. I would say the Earth system as a whole, because although these states can be typified by climate alone in terms of, and we have somewhat here by hothouse and Holocene-like and so on. But there's a whole bundle of other things in the biosphere that also correlate with those states. We thought it's easier for people to understand in terms of climate, but it is a little bit more complex than that. So we're talking about different states of the Earth system as a whole.
Right.
So in hothouse Earth, the biosphere itself is very different, and it's not a case of where the biosphere doesn't like the hothouse Earth state. It's not good for large mammals. But other parts of the biosphere will thrive in a hothouse Earth. Types of bacteria will thrive, smaller organisms will thrive, and so on. So, but it'll be a vastly different biosphere, as it was when the Earth was 4 or 5 degrees warmer back, say in the Eocene, which I think was about 16, 18 million years ago, and then further back from that, the Earth might have even been a bit warmer. So what we're saying is these are different states of the Earth system as a whole. They certainly can be characterized by global average surface temperatures as one of the metrics. And given that we are so focused on that in terms of climate change and the Paris targets, it's a really nice, simple metric to use to describe what's actually a more complex change in the state of the Earth system.
Okay, good. And so looking at this diagram, so we've got basically a temperature scale runs up here. So for example, in the middle here would basically be around what, pre-industrial sort of temperatures?
That's right. We put that in as pre-industrial.
Okay, and then what we've got on this axis here is sea level. And so effectively what happens if you follow the lines on the diagram, as the temperature increases, the sea level goes up. Okay.
Yeah, but there's lags in both directions. The temperature moves much faster, and the sea level slowly catches up, and that's why you don't see a circular. You see quite a stretched out, elongated figure, an ellipse.
Okay.
And that's different time scales of the two, but obviously they're linked. But it's not really one causes the other. It's a feedback system, obviously. Yeah. So that blue one in the lower left panel, this one down here, is actually the well-known glacial interglacial cycle of the last 1.2 million years. It actually goes back to about 3 million years, but in the last 1.2 million, it's had a periodicity of about 100,000 years. So you can track the temperature dropping, sliding into an ice age, and then sea level following a bit afterwards, till it reaches its minimum over on the left side of that lower circle there. So that's how it works. And then the system comes out of a glacial state about every 100,000 years. Temperature rises, sea level follows, moves to the right. Now notice that where we are in point A, which is pre-industrial, it's not today, it's pre-industrial. So think around 1750, we were down sitting at A. Mm-hmm. That's actually a little cooler than the maximum Holocene, or maximum interglacial temperature, by about 0.5 degree or so.
Right.
So in the Holocene about 7,000 years ago, it was about a half a degree warmer than it was in the pre-industrial.
Okay. Okay, so basically this relationship between sea level and temperature has been going on a 100,000-year cycle for between 1 and 3 million years.
Well, on the 100,000-year cycle for 1.2 million years.
1.2 million. Okay.
It was on about a 40,000-year cycle.
Okay. All right. So for the last million years, this has been the relationship between temperature and sea level.
That's correct.
And that is the time. I'm just going to close this window. There's some annoying person with a power tool. And so this is the sort of climate or the Earth processes, the Earth system state in all of the time that the human organism has actually grown up through the last million years of its evolutionary history.
Yes, that's true. And certainly fully modern humans, us, have only been around for 200 to 250,000 years. So definitely this is our home state of the Earth system, this so-called limit cycle between glacial and glacial states.
Okay, and really, so for the whole of modern humans, so 250,000 years or so, we've basically gone through two of these complete sort of glacial cycles, and towards the end of the last one, we had whatever caused us to trigger. But this is where the conditions were right for civilization to begin, and agriculture and towns and cities. And so, what's happened as a result of us putting all the carbon in the atmosphere is that we have now sort of flipped out of that state, and we're now effectively on the trajectory towards this hothouse. That's how I'm reading that.
So
okay.
we're sitting here at that little bowl marked B.
Yeah.
And so roughly we're about 1 degree Celsius above pre-industrial, which of course is what the contemporary observations are telling us. But of course the trajectory, given our CO2 emissions, which are still going up, is on that red line as you're showing there, up toward hothouse Earth. Hothouse Earth would be 4 or 5 degrees warmer, and that would be the uppermost of the IPCC climate scenarios.
Okay, now, and if we go to, and hypothetically, if we were 4 degrees above baseline, and that is a world which is incompatible with human civilization in anything like a form that you recognize it today. Is that right?
That's correct. You'd have to be an extremely brave person, in my view, to say that humanity could thrive or even survive in present numbers and level of well-being in a 4 to 5 degree hotter world. And reaching that within a century or a century and a half is sort of unheard of in Earth history.
And that's really the trajectory. So the RCP 8.5, or the business as usual, 3% average global growth based on fossil fuels, that will effectively take us to that place within a century. That's how I'm reading?
That's right. And so well, yes. And so again, the RCP 8.5 of the IPCC takes you to around 4 degrees by 2100, thereabouts. Right. There's quite a range, of course, of what the models, the worst range gives you 5, the best maybe 3 to 3.5, but a good average is around 4. But the interesting thing is when you use intermediate complexity models to simulate beyond 2100, up to 23, 2500, 3000, and you need to do this to capture sea level rise because it keeps going on for centuries and centuries. You start to get this bigger loop that you see in the upper right-hand panel of this diagram in terms of temperature then going above 4 degrees toward 5 or 6 or 7, say by 2300, and the Earth only starting to stabilize many millennia in the future after we've pretty much exhausted fossil fuels. But of course, we're way outside then this glacial interglacial limit cycle of the lower left panel. We won't go back into that. We'll be basically very close to ice-free. It'll take on order of 100 to 200,000 years for that broken red line to bring us back down. And that represents what are called the carbonate and silicate rock weathering cycles, which very slowly do take carbon dioxide out of the atmosphere. So what we're saying is we don't think there's any potential of a so-called runaway greenhouse effect that just keeps going, but we could go up to an extremely hot planet, exhausting most of the fossil fuels. And then it'll take a very slow recovery of the Earth system to come back down to something resembling what we've known in the past several centuries.
Yeah, okay. And so then you've got this little inner curly path here, and what I take that to mean would be a rapid decarbonisation of the global economy and a significant amount of CO2 drawdown to try and return, or to try and keep the planet from, keep the planet within this sort of space in the corner there. Is that right?
Yeah, so basically what we're saying here is, you can see it just brushes the 2 degree. We could probably still do that without CO2 drawdown if we get our emissions down really fast. That's 2 degrees. Yeah. If you want the 1.5, which would be even a slightly tighter curve than what we've drawn, then according to the IPCC, you will almost certainly need some level of CO2 drawdown from the atmosphere and storage in geological formations, so-called negative emission technologies. So basically what that tight inner circle is trying to depict is the 1.5 to 2 degree Paris target world, where we do stabilize the Earth well outside, by the way, the conditions we've known in the glacial interglacial cycle period, but certainly not a hothouse Earth, something that we may be able to at least survive in a reasonable condition.
Okay. And it would be safe to say, if it wasn't for us burning fossil fuels, that we would ultimately, sometime in the coming decades or centuries, go back into another interglacial, back into another glaciation, which itself would have actually been pretty bad for 7 billion humans.
Actually, what governs the speed of that blue circle, those arrows going around, is Earth's orbital parameters, because they trigger the changes, the loops in that circle. And when you look at the Earth's orbital parameters now, we are due for an unusually long interglacial. We saw one like it before, about 400 to 500,000 years ago. So all these circles do not have the same time frame.
Right.
So we're at a period where we would be on that upper bit, the Holocene-like conditions, for at least probably another 20,000 years without screwing it up ourselves. Right. So it's not permanently going into an ice age. So one thing that this diagram does not depict is the speed at which the Earth moves around. And it's not an even speed, right? Because it's in Earth's orbital parameters. So you can't put everything on one diagram, and you've got to keep it simple. Yeah. So that's one thing that doesn't appear very clearly in this diagram. But we would be in for another 10 to 20, I'd say closer to 20,000 years before we'd be heading for another ice age. And Paul Crutzen, who was the first person to recognize the Anthropocene and the fact we were out of the Holocene, and as an atmospheric chemist, he suggested that if we survive our excursion away from this system and get back down to something looking like an interglacial, we will become clever enough to develop what he called designer greenhouse gases that we could inject into the atmosphere at just the right amounts to maintain an interglacial state for even longer periods of time. But of course, that's a 20,000-year hypothetical.
Yeah, yeah. Actually, and this brings me back to one of the statements that I use. I wrote a paper recently I'm doing a Master of Business, so I wrote a paper the other day, and I referenced this document, but it's something in here, is it? Here, I'm going to highlight it. And it's this concept of stewardship of the entire Earth system, which really resonates with me, because the way I read this diagram is that if we just continue to burn fossil fuels, we're not being stewards of something, and a steward of something suggests active management. Okay, and so if we just continue to burn fossil fuels, we're not being stewards of the Earth system. But if we actively, and like you're saying, you design the greenhouses, that you design the greenhouse gases, that you have some sort of internationally agreed control mechanism to ensure that there is just the right amount of greenhouse gas in the atmosphere in order to achieve the state that we want on this planet, which ultimately would allow for a robust biosphere as well, which should ultimately be the conditions suited to the well-being of human civilization. That we need to, that because we've actually broken this thing, we now own it.
Yeah, that's a good way of putting it. And I think I would say, of course, this design of greenhouse gas ideas way, way, way into the future, and it was sort of a hypothetical that Paul put forward at that time.
Yeah.
I think in terms of stewardship, I would say the most important thing we need to manage now is ourselves. And we've proven to be pretty inept at managing ourselves. The present socioeconomic system we have is basically extremely destructive when you look at stewardship of the Earth system. So I think what we're seeing is that that little segment called A on this diagram, where we've left the glacial interglacial cycle and gone up to point B, where the little ball is, that has basically been driven mostly post-1950. That's the Anthropocene, the beginning of the Anthropocene trajectory, and it's been driven by the political economic system we've put in place after World War II. In other words, the liberal economic system where economic growth trumps everything else. Well, it certainly has been an extremely powerful paradigm, but it's also destabilized our entire life support system in the process.
Yeah. Okay, now I'm just going to move on to the other diagram in here, which is the one that I spent a little bit of time scratching my head over. Hopefully you can enlighten me. So if I can just give the layman's version, and then you can show me where I went wrong.
But first of all, this is, okay, you want to give me the layman's version first?
Yeah, if I can. So basically what I'm sort of understanding it in, the term that I read years ago is stability domains. So the idea of that if the ball was sitting in this loop here, so here's planet Earth back in time. This is in the Holocene back thousands of years ago. And this is time running forward. Here's the Anthropocene, here's time. And this is stability. So you've got a higher stability level up in here. But basically, if the ball was over here, then that's a relatively stable place, because in order to move the ball, you've got to sort of push it uphill. Whereas where it is here, it's less stable because you've got less distance to push it before it falls back into one of these states. But because we've got this condition now with the potential of the runaway effect or the positive feedback effects, as we sort of progress in time, we're actually becoming increasingly less stable, or more likely to actually just sort of run down into this hot well in the bottom there. Is that right?
Yeah, but basically this is really sort of a cartoon version of a stability landscape. It skates over a lot of the much trickier maths and so on. So basically, and what it doesn't do is it doesn't actually, the wells and the ridges and the valleys don't flex with time, which actually they should do if you wanted to animate it. For example, if we took the entire right-hand side away and said, let's just look at the glacial interglacial limit cycle that you see in the upper left of this diagram. In fact, if you went forward in time, this glacial valley would sort of flatten out and disappear for a short period of time, when the Earth would go into this little scalloped, warmer valley. And then very quickly thereafter, this little ridge to the left of the bowl there would disappear, and the glacial valley would reappear and deepen. And it would sort of oscillate between that at about 100,000 year cycles. Yeah. And so the real term that mathematically oriented Earth system scientists use is not really a limit cycle. It's called a pullback attractor, where the attractor really is the glacial state. We spend most of the time in the glacial state. And so they're because of Earth's orbit and feedbacks in the system, mainly because of feedbacks in the Earth system, we spend short periods of time up in these little, very short-lived valleys up there, and then fall back down again as the glacial valley reasserts itself. But of course, for us humans, those little valleys up there above the glacial are really important, because that's the only place we can thrive. Right. So basically what we've happened is instead of sitting nicely where the ball is in the upper part of that diagram, which we should do, by the way, for about another 20,000 years before that valley starts to disappear, as we just discussed. Mm-hmm. We've actually now started to push it out of that nice little valley, but away from a glacial. Yeah. Into, if you like, Earth system phase space that the Earth hasn't been in for quite a while, for at least 3 million years, probably longer. Mm-hmm. And so we don't exactly know what that looks like. We've drawn it as a very shallow valley, mm-hmm. and the Earth is sort of rolling around in that fairly erratically. Mm-hmm. But where we put it today at about 1 degree is that there is a valley just starting to form. Mm. And that valley is being formed by the fact that we are naturally now starting to lose carbon to the atmosphere. And that's due to things like the Amazon droughts and forest fires, the boreal forest fires, and so on. Soil respiration increasing with temperature, and so on. And so we're starting to generate this weak, shallow valley. But the further we push the Earth, and the big push of that arrow is not a natural formation of the valley, it's the fossil fuel emissions that is shoving the Earth over there. And the fact that the valley is starting to form are the natural responses of the Earth system to this.
Yeah.
And so the problem is, and the other one, of course, is loss of ice. Because as you lose ice, particularly sea ice, you uncover darker ocean water that absorbs more sunlight, it warms further. So we're starting to see a valley emerge from the intrinsic feedbacks in the Earth system. And as we push it further with fossil fuel emissions, we expect that valley to deepen as you get more feedbacks. And we're hypothesizing in this paper that there's some point at which these feedbacks become self-reinforcing, very crudely like a row of dominoes. Yeah. And that's what we call the planetary threshold. You see that mark there?
Yep.
Once the Earth system gets pushed into once the valley gets deep enough that we can't avoid that threshold, we still may be above it, but we can't avoid it, then we're committed to a hothouse Earth. So the point is, where is that fork in the road? We don't know where that is. That's going to require more research. But the other branch we call Earth system stewardship is just what we've been talking about, getting ourselves under control, changing our socioeconomic systems, and generating a new valley, a little bit deeper than the Holocene, a little bit warmer than the Holocene, one that we can stabilize so it doesn't fall into hothouse Earth. Now, we are, again, hypothesizing that that is not a natural state of the Earth system. Mm-hmm. It's going to require ongoing stewardship, mainly managing ourselves, so to speak, to keep the Earth in that stabilized Earth state. So again, what this is in my view, it's not a prediction. It's a risk assessment is really what we're talking about. Is we know enough about the Earth system to know that this is a credible risk. Yeah. This is what I would put it.
Yeah, and this planetary threshold is a point, sort of analogous to if you're in a canoe paddling away from a waterfall. You know, if you get too close to the waterfall, the velocity, you're just not going to be able to paddle fast enough. So if hypothetically all of your drawdown, it's just going to run away. Exactly. And that's a threshold that is basically defined more or less by an average global temperature. Is that right?
A range of global temperatures. That threshold is not a sharp point. Yeah. You can think of it more like a cataract or a cascade of waterfalls. That once you get close to them, you start rocking down, and once you're in them, you know, you're finished. But that's more what it looks like. And I sort of use a row of dominoes, but that's a very simplistic view of some pretty complex dynamics. The way to look at it is, we think that there are some of these tipping points in the Earth system that are vulnerable at 1 to 2 degrees. Arctic summer sea ice is one of those. Right. Some of the Antarctic summer sea ice is another one. Some permafrost melting, but not entirely. And so what we think we'll see is that these early feedbacks will then push the temperature up a little higher, which puts the conditions in place to possibly trigger further feedbacks. For example, Greenland ice. That's on its own, that's probably not vulnerable at 1.5 to 2, but it may be vulnerable 2 and 2 to 2.5. So if some of these feedbacks you see here start pushing the Earth from 1.5 to 2, you may see Greenland go there. You see Greenland is in the 1 to 3 range. Arctic summer sea ice in the 1 to 3 range, West Antarctica in the 1 to 3. So basically what you're seeing is those tipping elements that have strong feedback effects and are vulnerable in 1 to 3 tend to be polar ice in general.
Right.
Now, coral reefs is an important ecosystem for other reasons. It doesn't have a strong feedback to the rest of the Earth system. That's why you don't see an arrow coming from it. Right. But it's also vulnerable at 1 to 3.
I see. Okay. Okay, so let me just repeat that in my layman's terms. So basically, what we've got your tipping elements here, and so your temperature range 1 degree C to 3 degrees C above pre-industrial baseline average global temperatures. And so, for example, this yellow one, so somewhere between 1 and 3, the coral reefs basically fall off, but or die off. But when they die off, they don't have direct feedbacks into that temperature ranges again.
No.
Unlike, for example, if the Greenland ice sheet falls apart around the same temperatures, that then triggers issues around the thermohaline circulation, which itself could tip. So when the Greenland ice sheet falls apart and the Arctic summer sea ice, then basically that leads to a positive feedback of increased temperature because of your albedo and also your latent heat issues, which then feed into the thermohaline circulation, which then tips. And these things are interconnected with a larger thing, which is the falling apart of the East Antarctic ice sheet.
That's essentially correct. So what those two together do, the Greenland ice sheet and Arctic summer sea ice, is they obviously enhance regional warming in the northern high latitudes. We already see that. And that disrupts atmospheric circulation. We already see that with the disruption of the jet stream in the northern hemisphere. But then, as you say, they also, because of the Greenland ice sheet in particular, is putting a lot of fresh water onto the North Atlantic Ocean. That disrupts the thermohaline circulation down the North Atlantic Ocean. That does several things. It affects rainfall over the Amazon forest, because about half of the rainfall that falls on that forest comes from the Atlantic Ocean. It's advected in from the Atlantic. So it can affect the Amazon. It could potentially affect ENSO. But also, of course, it has this effect on the so-called bipolar seesaw in oceanic circulation between the North and South Atlantic. And that has a strong influence on the ice sheets in Antarctica. First of all, on the sea ice, but also on the upwelling and downwelling that occurs along the Antarctic coastline. Originally, we thought this was mainly a West Antarctic problem because of the fact that those ice sheets many of them are grounded below sea level. And so changes in ocean circulation could increase erosion and destabilization. Now we find that there are some big East Antarctic ice sheets that are also grounded below sea level. The Totten Glacier is the one that comes to mind. And that has enough ice that's about equivalent to all of West Antarctica. And already we see increased ocean seawater temperatures in the water underneath the tongue of the Totten. So there is concern. That's why this arrow now does not only go to West Antarctica, it also goes to East Antarctica.
Right, okay.
So, and this is some fairly new research that, again, it's not conclusive yet, but it's sending up warning signals that if we destabilize the northern high latitudes in terms of the ice and ocean circulation, it's going to have flow-on effects down in Antarctica.
Yeah, okay. Can you speak for a moment back to this Arctic summer sea ice? And so the concept of the blue ocean event, which is effectively where, actually, let me just go and find, I'm going to go and get the Charctic. Charctic interactive sea ice. Stand by a second. Okay, so this now, can you speak to the? You know, I'm sure you know this graph.
Yeah.
So this is who is this? Arctic Sea Ice News and Analysis, NSIDC. And so basically, this is showing the area extent of Arctic sea ice, and it's updated every day, right?
Yeah.
And so generally when this is set, it's set with 2012 showing, because 2012 was the year where it bottomed out to the lowest. And if you hit one of these buttons, for example, that one, not on there, which one is it? So anyway, so basically what we're seeing is this very sharp sort of decline, and it's one of the lowest. In fact, if you put them all on, show all.
Yeah, put them all on.
Just give it a second to. Right, so where we actually are now at this particular moment in time, it's actually the lowest amount of sea ice that has ever been on this particular day of the year since they started these records.
Yeah.
Okay, and so hypothetically, sometime over the next few years, that these lines will just continue to go down because it's warmer and there's more melting going on. That will get down to zero. Now, zero isn't zero. Is that correct? Because there's some. So my understanding is that this is to do with the area of the ocean with at least 15% sea ice. Now, I haven't been able to get my head around that concept. Can you explain that?
Yeah. So basically, it's if you've got more than 15%, that's part of an arbitrary number. Less than 15%, you consider it's close to ice-free. So 15 up to 100% would be what would be represented in those lines. So if a particular grid cell of that ocean it's blocked off into grid cells, if we can see from satellite imagery that grid cell has more than 15% ice, then it's considered to be ice covered. If it's less than 15%, it isn't. So that's really how you get ice extent, which is the vertical axis there in terms of, I think that's millions of square kilometers that they've got up there. So the point is, during the height, which would be February, March, which is the end of the Northern Hemisphere winter, you're seeing about 15 to 16 million square kilometers covered with ice. And of course, it naturally melts back. And the minimum is usually around September. So yeah, there you see the September minimum, which is the end of the Northern Hemisphere summer. And so year by year, decade by decade, that minimum has been dropping. Yeah. So historically, it was 7 or 8 million square kilometers. Now it's down to less than 4. And of course, there is an internal feedback in that the lower the ice extent is in the winter, the more dark ocean is uncovered, the more absorbs during the Northern Hemisphere summer, the warmer it gets, and that melts the sea back even more. So a lot of scientists think we've already crossed the tipping point. It's a good example of we're already being sucked toward the waterfall and we can't get out.
Yeah.
So that we're committed. Maybe it'll be decade and a half, 2 decades. We'll hit that summer where it hits zero, and you basically don't have any sea ice to speak of in September. So that's basically what this graph is showing you.
Okay, and there's one other thing, because it's not just the I actually came up with this idea on my own, if you like, and then later on, it was some time later that I actually found references to it in the scientific literature. That when you lose the ice, you get 2 things happen. Firstly, is you reduce the albedo, which is the white reflective surface which bounces sunlight back into space. But the other thing that happens is because of the, and I don't know how to use the words properly, but because of the latent heat of fusion, I think is the expression, that it requires large amount of energy to turn ice into water. That when the ice goes away, the heat which has been brought into the Arctic Ocean by this conveyor belt, so it's taking the warm water from the equator regions and bringing it up into the Arctic, where a lot of that heat is being used to melt the ice. But when there's no more ice there, that heat will actually warm the water. Is that correct?
Yeah, I haven't really myself seen that figure or amount of heating compared to the direct albedo effect. But of course, there's another issue there that scientists are worried about, and that's the thermohaline circulation, which of course pushes way up past Norway, the so-called Gulf Stream. The water cools there and densifies, drops down, and that acts as sort of like a pump for the Northern Hemisphere or the Northern Atlantic thermohaline circulation, ocean circulation. But as you're putting lenses of fresh water on top of that, which you do when you melt the ice, that makes it harder that's less dense than seawater, makes it harder for that downwelling to occur. And there's concern, of course, that you're going to shut down the upper branch of that current and lead to some regional cooling when you shut off that warm surface ocean current that comes up between Iceland and Norway. So there are all sorts of flow-on effects that may occur as you change the cryosphere, the ice up in the northern high latitudes. So yeah, the heating effects are certainly important as well.
Yeah, And so my reading also is, and again, this is how I sort of communicate it to people to try and make it really, really simple. And sometimes it's a little bit rubbery science because it's so simple. But when we get this blue ocean event, or when we lose as we lose the ice, then so effectively you end up with it gets warmer up here. And so my understanding is that this concept of the dipole, which says that we've got warm temperatures down around the equator, and we've got nice and frosty cold temperatures at the top in the polar region. And it's that temperature difference, the delta between the warm and the cold, that effectively drives the air circulation, which drives the climate system of the northern hemisphere. And that as we get more and more of this melting, we get increased heating, the delta goes down, the temperature difference goes down, and then that destabilizes the entire weather system. Have I got that right?
Well, that's pretty much right. I would say rather than the entire weather system, I would say the circumpolar circulation is really what gets destabilized.
Okay.
The so-called jet stream.
Okay.
So the way to think of it is the jet stream is a circumpolar circulation of air in the northern hemisphere, goes around the pole, sort of in the northern high latitudes. Until we destabilized the climate, it was fairly well restricted and didn't oscillate north and south very much. But so that temperature differential, the delta that you talked about, acted as a guardrail, so to speak, to keep the jet stream, to keep the cold air north and the warm air south.
Right.
But as you reduce delta, as you reduce the temperature differential between the equator and the North Pole, that weakens that guardrail effect, and the jet stream, the circumpolar circulation, starts wandering. And some people have called it the wandering jet stream. And so what that tends to do is it tends to draw very much warmer air up north, but drag colder air down south. And so you get this counterintuitive effect there you see on what you're showing there across North America, is you can bring some warmer all the way up into, well up into Canada, and then drag down cold air down to the southeastern United States, and it snows in Georgia, and people say this is the end of global warming or something, when in fact they're simply misinterpreting what's going on. One of the most dramatic cases I've seen of that's actually over Europe, where I think it was either this year or last year, Sweden was recording temperatures in the north that were 30 degrees Celsius above average, not 30, as it was bringing up very warm Mediterranean air all the way up, or tropical Atlantic air all the way up past northern Sweden. So basically, that's what's happening there. And there's a lot of these really lovely diagrams showing what should be a nice, fairly even jet stream now wandering north and south.
So this one here, so that's trying to find there.
There's probably some good animations of showing what happens here, but
well, let's see if we go there. Okay, let's leave that for a moment. Okay, that's good. And so that jet stream then, and so like you just mentioned that in Sweden, it got to 30 degrees Celsius above 30 degrees Celsius above what it would have, it's sort of average for that time of year, because of one of these big loopy things.
So that happened over a few days. I think it was earlier this past winter or the one before. I can't remember particularly. It was one of the last two winters anyway. But it was a remarkable temperature.
I've been involved in climate change since 2000 when I started carbon auditing for businesses under a program called the Greenhouse Challenge, and so for most of that time it's actually been a bit of a lonely existence, because it's quite an esoteric, well, for most of the last 20 years it's been quite an esoteric field. Not many people really got into it, but something happened, I think, in the northern summer of 2017. I was over in the UK staying with my family, spent a lot of time in this comfy chair with a bottle of wine and the cat watching the news. And I was just watching this constant barrage of hurricanes come through. This is when we have Maria and Irma and Harvey, the 5 big ones. And it seems to me that something has shifted in the last 2 years in a very, very noticeable and dramatic way. Is that an observation that you've made, that you can attest to?
I would describe it as being a spike in a longer term trend. toward more intense tropical cyclones. There's some good data out now, which encompasses 2017, showing that the fraction of cyclones that are category 4 and 5 has gone up quite steadily over the past several decades. But certainly 2017 was a spike in that record.
Okay.
So it's part of a longer term trend. Again, this has been predicted by the basic physics for a couple of decades at least. So what we're seeing is a drop off in the number of cyclones at the lower end, the category 1 and 2s, and an increase in category 4 and 5s, and also an increase in wind speed in those intense ones. We're getting some really powerful cyclones now that we haven't seen for a while. So basically, the very simple explanation is that because the sea surface temperature is changing as well as the atmospheric temperature is changing, it's changing the conditions in which these cyclones form. So it's actually decreasing the genesis of cyclones, but when they form, they've got warmer ocean water to draw from, so they become more intense. So there are two different processes at work here. One is genesis and one is development and strengthening. And they're both affected by climate change, but in different ways.
Yeah. And it wasn't just the cyclones. It wasn't just those cyclones that appeared to have shown this uptick in intensity. And maybe it's because I was just looking at new information, like I started to, follow certain YouTube channels, for example. But it just seemed that there was this, in the last couple of years, this significant uptick overall in the intensity of the wildfires, the flash floods in particular, and the big non-flash floods and the flash droughts. And so, I mean, the point is, as you're pointing out, is that because we keep putting all of this heat in the system, there's this linear increase, but it's not linear because it's jumpy and spiky.
Yeah.
Overall. Yeah. And so we're going to see, there's going to be some totally freaky years where it seems to be going crazy everywhere. And then the next couple of years, it could actually just be kind of normalish.
Yeah. And so the problem is you've got to have that long-term perspective. In my view, you got to take at least 3 decades into account if you want to look at a trend.
Right.
And so a lot of people quite mistakenly will look at a couple of years after a really bad year and say, well, look, it isn't changing much now. Therefore, there's nothing to worry about. There isn't much to this. So one of the absolutely cardinal sins that people make is taking too short a time frame to look at what's happening. The good rule of thumb is at least 3 decades if you want to see a trend that can possibly be linked to the longer term shifts in the climate system.
All right. And look, and on the subject of time, we've actually come to the end of our hour, and I'm going to clip it off here. But Will, I feel like this conversation has really just sort of scratched the surface in a way, because your knowledge of these things is so deep, and the things that you are most knowledgeable on are the things that I'm most fascinated by. And so I'm hoping that I can have another chat with you like this another time, and I'll be better prepared. We'll have some really good diagrams and some videos, and we can do some drill downs and really get the benefit out of this really awesome technology.
Okay.
Is that all right?
Sounds good.
Okay.
Sounds good.
Thank you, Will, and I look forward to our next chat.
Okay, thank you. My pleasure.
Okay.